Exponential functions. So in this video, we're going to learn about exponential functions and their properties. So first, we're going to define what is an exponential function. It's any function in the form b to power x, and notice the exponent is the variable. And b can be less than 1, and it has to be positive, or it can be greater than 1. And we're going to see when it's less than 1 how the graph looks like, and when it's greater than 1 how does the graph look like. So an exponential growth is when b is greater than 1, and this is the graph of y equal b to power x when b is greater than 1. Notice the horizontal asymptote is y equals 0, and we have the y-intercept is 0, 1. So again, we have the graph of y equal b to power x, and in this case, we have b is greater than 1. Now we're going to see the case when b is less than 1. So this is the graph y equal b to power x when b is less than 1. In both cases, we have the horizontal asymptotes y equals 0. So keep in mind also the domain is negative infinity to positive infinity, and the range is 0 to positive infinity. We're going to start with the first example. We need to graph y equal 2 to power x. So we're going to substitute several values for x in my function to get the value of y. So we get some points. We're going to plot them on the graph and connect the points. So when x equal negative 3, that's going to be y equal 2 to power negative 3, that's 1 over 8 or 0.125. When x equal negative 2, y equal 2 to power negative 2, that's 1 over 4 or 0.25. When x equal negative 1, y equal half, 2 to power negative 1. When x equals 0, 2 to power 0, that's 1. 2 to power 1 is 2, and 2 to power 2 is 4. So we collected some points. We plot several values for x in y equal 2x, and we got the value of y. Now we can graph y equal to 2 to power x. So we're plotting the points to get the graph. Then we're going to connect them to get the graph. So this is the graph of y equal 2 to power x. Again, the domain is negative infinity to positive infinity, and the range is 0 to positive infinity. Keep in mind, y equals 0 is the horizontal asymptote. Now we're going to see transformations on the exponential function. So this is the graph of y equal 2 to power x. Now this is the graph of y equal 2 to power x minus 1. So it's got shifted one step to the right. So notice the x values. It was 0, it became 1. When it was 1, it became 2. So it got shifted one step to the right. Another example of transformation. So we have the graph of y equal 2 to power x. Now this time we're going to do horizontal shift. So this is the graph of 2 to power x plus 2. So we moved our graph 2 units up. Now for 2 to power x, y equals 0 was the horizontal asymptote, while for the graph of 2 to power x plus 2, y equal 2 is the horizontal asymptote. So keep in mind also the horizontal asymptote get lifted 2 steps. Now we have y equal 4 to power x. First we're going to complete the table. We're going to substitute x by the values we have. And first we have x equal -3, so 4 to power -3, that's 1 over 64. When x equal -2, that's 4 to power -2, that's 1 over 16. And 4 to power 0 is 1, 4 to power 1 is 4, and 4 to power 2 is 16. And 4 to power -1 is 1 over 4. So we have points, we can plot them. To get the graph of y equal 4 to power x. Also here, the horizontal asymptote is y equals 0. Now we have the graph of y equal 4 to power x. And we're going to do some transformation. So that's the graph of 4 to power x plus 2. So notice my graph moved to the left 2 units. Still, the horizontal asymptote is y equals 0 in both cases. So the transformation of the parent function y equal b to power x is the same as any other functions. So the rules of transformations, the horizontal and the vertical and we have the orientation and shape. So it's similar to any function, even if it was exponential function. Now exponential decay is when b is less than 1 and b has always to be positive. Also we have the x-axis is the horizontal asymptote and the y-intercept is 0, 1. So another example, we're going to substitute x by -2. So that's 9. When x equal -1, that's 3. When x is 0, that's 1. When 1, y equals 0.3. And when x is 2, y equals 0.1. We have Euler constant, refers to the mathematician Euler, Leonhard Euler. And this is the graph of e to power x. Also, we have y equals 0 is the horizontal asymptote, and we have the y-intercept is 0, 1. E is a constant that's equal to 2.718, etc. It's an irrational number, and we can find it in the calculator. So this is the graph of y equal to power x, and we're going to see also transformation. If I want the graph of y equal e to power x minus 2, I just have to move my graph 2 steps down. Keep in mind here, y equal negative 2 is the horizontal asymptote. The domain is negative infinity to positive infinity, and the range is negative 2 to positive infinity. This is again the graph of y equal e to power x. This is y equal e to power x minus 3, so it got shifted to the right 3 units. So this is the graph of y equal e to power x. If I want minus e to power x, is going to be as such. So this is the graph of y equal minus e to power x. Now also we have the formulas for compound interest. So also we see the variable in the exponent. So we have these two important formulas for compounding periods and for continuous compounding. And n is equal to when we have semi-annual compounding, n equal 4 when we have quarterly compounding, n equal 12 when we have monthly compounding, and n equal 365 when we have daily compounding. So find the accumulated value of an investment of 10,000 for 5 years at an interest rate of 5.5% of the money. Keep in mind the time always has to be in years and the rate has to be written as a decimal. Compounded semi-annually is going to be as such, n equal to, and notice r is 0.055 because it's 5.5%, and p is the money I'm investing, that's 10,000, and time is 5 years, and n here is 2 because it's semi-annual. Compounded quarterly is going to be 10,000, and n is 4. Monthly, n is 12, and continuously, this is the formula, and the rest is calculations.